Hello everyone, I am Paramita Saha. I am a master's student from Electronics and Telecommunication Engineering Department, Jadavpur University, Kolkata. The topic of my today's talk is smart beam steering with a slot-loaded miniaturized patch antenna. Here are the outlines of my talk. First of all, I will focus on the patch antenna and its miniaturization techniques. After that, I will discuss the proposed slot-loaded miniaturization technique of the patch antenna. Later, I will discuss the designed beam steering network consisting of power divider circuit and phase shifter circuit. At the end, I will demonstrate the beam steering operation with the proposed antenna. Microstrip patch antenna is a well-known antenna which is popular for the spaceborne applications like aircraft, spacecraft, satellites, radar applications, etc. It has some special features like it can produce linear as well as circular polarizations. It has a planar and compact geometry, and that's why it is very easily integrated in microwave circuits. Its fabrication cost is very low and it is also mechanically robust. The miniaturization of microstrip patch antenna is a technique to reduce the frequency of operation of the antenna without increasing the antenna dimensions. Some of the conventional miniaturization techniques are shown here, like using shorting pins, using metamaterials, introducing slots on the patch, using high permittivity material, etc. At first, a reference antenna is designed for the 5 GHz. The antenna is designed at a FR4 substrate with a thickness of 1.6 mm. The dimensions of the antenna is given in the figure. Coaxial feed line is used to excite the antenna. To miniaturize the reference antenna, a horizontal slot is used and it is placed asymmetrically on the patch. The slot has a length of Ls and width Ws, and it is placed at a gap of Gs from the top of the patch. The idea was to introduce a capacitive loading and rearrange the current path of the antenna so that the same geometry can resonate at a lower frequency. Some optimizations are done for the slot. Here, the effects of slot length is shown. The slot length Ls is varied by keeping the other dimensions of the antenna constant. Without the slot, the reference antenna is resonating at 4.84 GHz. By using the slot, the antenna is resonating at a lower frequency. From the figure, we can see that by increasing the slot length from 5 mm to 15 mm, the resonant frequency is shifted down from 4.66 GHz to 2.56 GHz. At Ls equals to 15.9 mm, the antenna is resonated at 2.45 GHz. The effects of slot width are shown in this slide. The slot width is varied by keeping the other dimensions constant. From the figure, we can see that by increasing the slot width from 0.5 mm to 2 mm, the resonant frequency is shifted downward, but at the same time, the impedance matching of the patch is degraded. The effects of slot gap is shown in this slide. The slot gap is varied by keeping the other dimensions of the slot constant. From the figure, we can see that by increasing the slot gap from 0.5 mm to 2 mm, the resonant frequency is shifted down, but at the same time, the impedance matching of the patch is degraded. The surface current distribution for the proposed patch at 2.45 GHz is shown in the figure. It can be observed that most of the current surrounds the slot. Hence, by increasing the slot length and the slot width, the length of the current path is also increased, and the resonating frequency is decreased. Also, the impedance at the feed point is affected by placing the slot near to the feed point, and it degrades the impedance matching of the patch. From the numerical investigation, LS equals to 15.9 mm, WS equals to 1 mm, and GS equals to 1 mm are considered to design the patch at 2.45 GHz. The proposed patch is resonating at 2.45 GHz with only 23% area of that of the conventional patch at 2.45 GHz. Only the directivity is slightly reduced from the reference antenna. Beam steering is a technique to steer the antenna beam at the desired location. It is a very well-known technique, and with the beam steering technique, the antenna beam can be steered towards the desired location. Some of the conventional techniques are shown here, like reflect array technique, passive array technique, using sectorial antenna, etc. To facilitate the beam steering operation, beam steering circuit is designed, which is shown in the figure. A 1x8 array of the proposed patch is designed. A 1x8 power divider, corporate feed power divider circuit is designed to excite the antennas with a single excitation. A 1x8 phase shifter circuit is also designed to provide progressive phase shifts by individually increasing the length of each feed line of each of the antenna. The beam steering circuit is designed in a double layered FR4 substrate. The 1x8 antenna array is placed at the top layer of the substrate, and the power divider and phase shifter circuit is placed at the bottom layer of the substrate. A common ground plane is placed in the middle. The power divider circuit for the first two antennas is shown in the figure. The first input feed line has impedance of 50 ohm. This line is divided into 200 ohm lines to divide the input power into two equal parts. This 100 ohm line has to be fed to the 50 ohm line again. So, to match for the impedance matching of the 100 ohm line, to match the impedance of the 100 ohm line with the 50 ohm line, a quarter wave transmission line of impedance 70.7 ohm is placed in between them. Length of 50 ohm line doesn't play any role in the design, hence are adjusted according to the placement of the antenna and the underlying circuits. The phase shifter circuit for the first two antennas are highlighted here. It can be observed that extra length is added to produce an additional phase shift. The extra length is added in the feed line of the second antenna to produce an additional phase shift over the feed of antenna 1. Therefore, both antennas are fed with signals of identical magnitude of A0 but with different phases. Similar phase shift circuits are used for the rest of the antennas. A phase shift vector phi v is generated which to summarize all of the extra lengths that is used for the phase shift operation. The radiation pattern on phi equals to 0 degree plane, that is for zx plane, are plotted in the figure. The phase shift vector phi v is multiplied by a constant MUL that would change the relative phase difference among the antennas. The average phase shift in antenna excitation for different values of MUL and the direction of maximum radiation are summarized in the table given below. Maximum plus minus 22% tilt is observed around the bore side by varying the input phases of each of the antenna elements. Here are the conclusions. A smart beam steering technique is investigated for ISM band application at 2.45 GHz. A slot-loaded miniaturized patch antenna is designed, and the patch is radiating with only 23% area of that of a conventional rectangular patch at 2.45 GHz. To facilitate the beam steering technique, a 1x8 array of the proposed patch is designed, and a 1x8 corporate with power divider phase shifter circuit is also designed. A maximum of 22 degree tilt is observed with the array by varying the input phases suitably. To improve the work, an electronic phase shift circuit can be used. To achieve higher steering angle, a larger array and different array elements can be used. A fabricated prototype is to be done for the experimental validation. I would like to thank the organizer of SPCOM 2022 IISc for providing the platform of publication, coordinator of VLSI Design and Microelectronics Technology, ETC, Jadavpur University, Mr. Jagabandhu Das for his excellent technical assistance and guidance, Professor P. Venkateshwaran for considering me in his lab and by providing research facilities and for his parental guidance. If you have any question, you can email me in the given email ID. Thank you.